In the last lecture, we talked about the hydrogen atom and its different orbitals, and those orbitals had 3 quantum numbers associated with them. In this lecture, we're going to see there's actually one more feature we need to pay attention to, which is electron spin, that adds a 4th quantum number to the state. And then we'll also talk about how this leads to electron pairing. So in particular, we'll talk about electron spin, spin quantum numbers, and the Pauli Exclusion Principle. It turns out that there are 2 flavors of electrons in the universe. The 2 flavors differ in something that we call electron spin. So electron spin doesn't have a great interpretation that we can think of readily. You might think of it as something like a spinning globe, whether it's spinning clockwise or counterclockwise, but that's not really correct. It's some inherent quantum mechanical angular momentum associated with these electrons, but it doesn't really have a good macroscopic interpretation. But the key point is that there are 2 possible spin states with the 2 possible angular momentum, one that we call spin up and one that we call spin down, and these have opposite angular momenta. And so to see this experimentally, we can do something called the Stern-Gerlach experiment. And so in this experiment, we have a beam of silver atoms being shot out and passed through a magnetic field. And so silver atoms, as we'll talk about later on, have 47 electrons, which is an odd number of electrons. And so it turns out that only one of those electrons is unpaired. All the others are paired up and sort of cancel each other out in terms of their spins. So we have one unpaired electron with a particular spin. That spinning electron, that angular momentum of the charged particle, creates a local magnetic field. And that local magnetic field then interacts with the permanent magnet here that beam is passing through. And depending on the nature of that field, it's going to interact differently. So the spin-up electrons and their local magnetic field will interact in a different manner than the spin-down ones do when they pass through this magnet. And so the beam gets split in 2 because we have roughly half spin-up and half spin-down. And so to describe this, we define the spin quantum number m sub s with a value of either plus a half or minus a half for the 2 possible angular momenta. But often, for simplicity, we just call these spin up or spin down. And as we'll see later in this lecture, it often doesn't really matter whether an electron is spin up or spin down for most of the things we're going to talk about in chemistry. It's mostly important just to talk about whether things have the same spin or opposite spin. We don't care so much about the specific details of whether it's spin up or spin down. Because of spin, it turns out we actually need 4 quantum numbers to specify the state of an electron in an atom. First, we need 3 to specify the orbital, right? We have the principal quantum number, we have L, which determines the shape, and we have m sub L, which determines the orientation. Those just specify the spatial orbital, but the 4th quantum number determines the spin, whether the electron is spin up or spin down. And so, for example, what 4 quantum numbers specify a spin up electron in the 1s orbital, which we might draw schematically as something like this, with a 1s orbital with an upward arrow indicating spin up? Well, we could represent that as an n equals 1, because it's a 1s orbital, L equals 0, because it's an s orbital. For s orbitals and L equals 0, the only possible m sub L value is 0. And so it's a 1, 0, 0 to specify that it's a 1s orbital. And m sub s is plus a half, indicating it's a spin-up electron. So those are the 4 quantum numbers corresponding to a spin-up electron in a 1s orbital. Let's do another practice. Which of the following orbital diagrams represents the electron specified by the quantum numbers n equals 3, L equals 2, m sub L equals minus 1, and m sub s equals minus a half? Pause the video, attempt the solution, and hit play when you're ready to hear it. Okay, so we know our principal number is 3, so we know it's going to be an orbital in the n equals 3 shell. L equals 2 corresponds to d orbitals, right? L equals 0 corresponds to s, L equals 1 corresponds to p, and L equals 2 corresponds to d. M sub L says it's going to be in one of the particular orientations. For this example, it doesn't really matter which of the particular ones it is. It's one of the d orbitals. and m sub s is equal to minus a half. So it's going to be a spin down electron. So we're looking for the example here where the electron is in a 3D orbital with a spin down. And we see that right here. So the answer here is E. Let's try another example. Now, which orbital diagram represents the electron specified by these quantum numbers? N equals 2, L equals 1, M sub L equals 0, and M sub S equals plus a half. Again, pause the video, attempt it, and hit resume when you're ready. So in this case, again, we have N equals 2, so we know we're in the N equals 2 shell. L equals 1 corresponds to a p orbital. It's M sub L equals 0, which tells us it's one of those orbitals in the p shell, just one of the particular orientations, and M sub S tells us it's spin up, because it's positive 1/2. So the only one here, which is a 2p orbital with spin up, is answer C. Electron spin isn't very interesting when you just have one electron. It gets far more interesting when you have multiple electrons in a single atom. And that's because of something called the Pauli Exclusion Principle. And so I'm going to give you two equivalent statements of this principle. The first is that no two electrons can share the same orbital and have the same spin at the same time. Alternatively, no two electrons can share the same four quantum numbers N, L, M sub L, and M sub S. And these are equivalent because, of course, N, L, and M sub L determine the orbital, and M sub S determines the spin. So if you have the same set of quantum numbers for all four, then you're going to have the same orbital and the same spin. But this has some really profound implications. And so first off, because of this, and because there are only two possible spin states, for any given orbital, any set of the first three quantum numbers, there's only two possible electrons that can be in there, one with spin up and one with spin down. So this is why electrons pair up in orbitals. There's a maximum of 2 electrons per orbital. And because of that, we get the filling of the orbitals that leads to the periodic table. We're going to have a couple lectures on that following this one, but just here's one example for the fluorine atom. This is the electron configuration for a fluorine atom. We fill 2 electrons in the 1s orbital, 2 in the 2s, and then 5 in the 2p's, spread out over all 3 2p's. And the reason we do this is because of Pauli exclusion, we can never put more than 2 electrons in one orbital. Because recall, the 1s orbital is the lowest energy. If we could put more electrons in an orbital, we'd put them all in this 1s orbital, but we can't. We have to spread them out because of Pauli exclusion. And so that's what leads to this sort of filling, and we'll see leads to this structure of the periodic table. It also turns out that the favorable interactions derived from electron pairing are what drive chemical bond formation, as we'll see later on in the course. By convention, we usually assign unpaired electrons to be spin up. So it's arbitrary whether we draw an unpaired electron to spin up or spin down for most purposes in chemistry. Now occasionally you might be doing something like the Stern-Gerlach experiment where you could actually distinguish based on how the beam splits. But for most of our purposes, we really don't care whether it's spin up or spin down. So we will go ahead and pair up all the electrons that can pair up, and then any leftover ones will be unpaired. And so then we have a choice. Do we draw the unpaired one as spin up or spin down? And like I say, it doesn't really matter, but by convention, we're usually going to draw it as spin up. But both of these configurations would have the same energy. However, if you have multiple unpaired electrons, then the spins can matter. And not in the absolute sense, but in the relative sense. And so consider a configuration like this, where we have multiple unpaired ones. This configuration or this configuration, where these unpaired ones are all spin up or all spin down, are equally correct. Doesn't really matter which one you use, though again, we would typically use the spin up version by convention. But either of these lower two configurations, where I have a mixture of spin up and spin down, would actually be incorrect. These would actually have different energetics and be a different electronic state than those. So the take-home message is, when you're working with these sorts of diagrams and thinking about unpaired electrons in their spins, you want to pay attention to how many paired versus unpaired electrons you have and their relative spins. And if you have any excess spins after you've paired everything up, you want them generally to be spin up by convention. So to summarize, we've seen that electrons have two possible spin states, spin up and spin down, and these are specified by the fourth quantum number m sub s, which can have values of +0.5 or -0.5. The Pauli exclusion principle causes the electrons to pair up in orbitals, and we're going to see soon how that leads to the periodic table. And by convention, any unpaired spins are typically going to be assigned to be spin up